Buenos días a todos.
Good morning, ladies and gentlemen.
Gracias. Buenos días a todos. Bienvenidos a esta mesa de redonda.
Welcome to this round
Como es de
table.
esperar, la adecuada gestión de los riesgos
As can be expected, in order to manage catastrophic risk, we need to estimate loss in order to reflect the real exposure of the insured risks. We're going to talk about the models that are used for the analysis of vulnerabilities. To this end, we have invited a series of panelists that are experts in this field. We have Derek Wolpers to my left, senior treaty underwriter of Swiss Re. I have to my right Juan England, managing director of Willis Re, and Michael Sprangler, representative in Europe. Welcome to all three of you, and thanks very much for being here with us today. Without further ado, I'd like to give the floor to Juan England. He's an expert in the assessment of seismic risk, and he has broad experience in the analysis of catastrophic risks. He's going to explain to us how the vulnerabilities are assessed and measured. Thanks very much, Josefina. Good morning, everyone. It's a pleasure to be here in this MAFRE Global Risk Seminar. And for me, it's an honor and a privilege to talk to you about this topic that is becoming increasingly important when quantifying risks, namely in the insurance and reinsurance market. The title of my presentation refers to the representativity of this catastrophic risks. I've been taking a look at the pictures that have been hung out in the launch, and we've seen some pictures of the damages caused by Mother Nature. And the idea is to represent these risks using a numeric model. That in itself is an extremely complicated task. I've been using these models for 9 to 10 years, and I'm a big fan of these models. But at the same time, I tend to criticize them very, very often. Today, in my presentation, I'm going to try to explain to you how these models are developed in order to help us model these risks. My views will be completed by the presentations of my fellow panelists. Perhaps my talk is going to be more theoretical. Let me talk to you about the origin of these catastrophic models. Some people say that we're still at an embryonic stage, and that's true. They started to be developed in the 90s. They're only 30 years old. It's not like actuarial sciences or mathematics that have a very long history. But before catastrophic models, this quantification of risks was based on experience. So we used the statistic methods, actuarial methods, in order to try to simulate future losses at high return periods. If we analyze an incident rate for the upcoming 20 or 30 years, if we're lucky, we're talking about a briefer period of time, but this methodology allows us to identify those potential events, catastrophic events. Coinciding with the Andrew hurricane in 1992, we started to understand that we had to use a different methodology that would be based on geographic exposures, with the ultimate goal of simulating hypothetical events, simulating, that is, thousands and thousands of events in order to be able to model them. It'll help us understand how to design our insurance and reinsurance products. So, as you can see, the history is short, and the main conclusion that we can draw at this point is that models are models at the end of the day, and we need to understand their limitations, but the main message that should come across is the importance of the discipline and the standardization in the management of catastrophic risk. Thanks to this model, this has been possible during the past 30 years in the world of insurance and reinsurance. As I was saying, we've been working on this during 30 years, and the aim of this slide is to explain to you when these models were developed and the different generations that exist. We're using the third generation of catastrophic risk models, and this line plots all of them. And each time that there is a hurricane, an earthquake, these models have helped us understand the limitations of these models. So now we are at a third generation of catastrophic risk models. At the beginning, we used deterministic models that modeled historic events and aim to analyze the as-if loss. But then we had the probabilistic models that started to simulate many events with frequencies and probabilities in order to try to identify those extremes. And nowadays, we have new suppliers and new platforms. At the beginning, there were 3 suppliers. Now we have 7 suppliers. So this is an industry that is growing as well. Nowadays, we see that more than 90% of the world GDP is covered by these models. So in any of these territories, we can simulate an exposure and quantify and measure that catastrophic risk of an earthquake or hurricane, regardless of whether we're talking about an insurance portfolio or an individual product. What matters most is that you understand that this industry started developing earthquake and hurricane models. Those were the main priorities. But now we have flooding, tsunamis, tornado models. But this is something that has arrived at a later stage. And to model the risk of hail and flooding is much more complicated. We're still working on this. We're still at an experimental phase. In the case of hurricanes and earthquakes, the model is pretty advanced, although it has some limitations. But now we're trying to model new risks, new hazards that haven't been quantified or measured up until now, or that didn't have an associated model. In 2012, we learned many lessons regarding these risks due to what happened in Thailand with the flooding, the tsunami in Japan, the liquefaction effects of the earthquake in New Zealand. So nowadays, we not only simulate the main hazards, but other hazards that had not been modeled in the past as well. I wanted to start with some initial considerations before I go into the crux of the matter. Each time I analyze a portfolio, each time I analyze a specific model, I bear in mind that models are developed today based on scientific grounds and on engineering grounds. And this is a great advantage because the research that exists regarding earthquakes and hurricane is very, very advanced. And those models grasp the science that already exists in representing the vulnerability and the risks and hazards. However, models need to be calibrated, as all models. And these models are calibrated using historical events, such as past earthquakes or hurricanes. The challenges in this calibration process are that the insured losses are lower, much lower than the economic loss. suffered by the country or the region that is affected by that disaster. So trying to calibrate a model in which you have economic and market information as well is in itself very challenging, and we need to understand what those challenges are. And as all model, we also need to understand the assumptions and the limitations. And since these models are based on exposure, the information that is used is very, very important. In each model, we need to screen the information, understand that we need to discriminate information as well. In spite of these limitations and constraints, these models have led to a discipline in the management of catastrophic risks in the industry of insurance and reinsurance. Nowadays, we're capable of collecting better information, more accurate information, and there's a greater understanding about this kind of risks. And if we compare the number of insolvencies in the insurance sector between 1992 after Andrew and 2005 after Katrina, we see that there are great differences. And this discipline has helped us enormously in managing and handling catastrophic risks. As for the vulnerabilities, it's very important that we understand and represent what models represent. In my next slides, I aim to show you the sensitivity of models to the information that is fed into them. This slide depicts the situation in Colombia using the 4 available models in the industry. And it's the same risk. In this case, we're talking about a risk with particular activity characteristics, construction characteristics, and we've covered the entire territory that is modeled. Where you see the darkest or reddest color is where the model is giving us higher vulnerabilities or loss than in other areas. So what we can observe and conclude is that the geographic location, and these are models based on geographic locations, is very, very important to represent the risk to which a region is exposed. And secondly, all models can yield different results. And that's something very interesting as well, because we conduct the modeling analyses and we obtain 4 or 5 results that differ from that of the modeling companies. And we need to understand the limitations of each model in order to be able to provide advice and to define what model is most appropriate, most accurate, and represents best that particular risk. In terms of activities, and this is an issue that is perhaps most relevant considering the subject matter of this conference, and this is the fact that each risk is associated to different activities. Models are calibrated based on economic loss, and they are governed by average loss. So when we calculate the economic loss, we do this based on a series of risks that are quantified. And based on this, we calibrate the model. And depending on the calibration, we will obtain different results. What is most important is that we define as accurately as possible the activity, the type of construction, the features and characteristics of this risk. This is what we call the vulnerability curve. The vulnerability curve is a parameter designed by the engineering and the calibrator, and the idea is to depict the physical damage that a structure will suffer and depending on the intensity of that threat or danger. Here you can see on the slide that there are 30 curves to depict the different kinds of activities, and it is very important that we define those activities as accurately as possible. Depending on the level of accuracy, we will obtain one result or another. In the case of complex industrial risks, these curves, vulnerability curves, are specific, and the aim is to establish a definition that is more specific than that helps us define the activity in a detailed manner. What we must do is to assess whether these curves represent what the engineers see out on the field. That is why it is very, very important to establish dialogue with the engineers to assess whether these curves really represent the reality out there. Here we cover from treatment plants to cooling plants, energy or power plants. The idea is that we defined a great number of risks in a highly defined manner. When we're talking about industrial risk and we're talking about a more standardized portfolio, we can use these models as well. What happens if you don't define the type or year of construction? As I told you, the models are based on scientific and engineering grounds. So if we model a risk, depending on whether it's, let's say, a brick risk or a timber risk, the results will be different. So it's very, very important to feed into the model the information regarding the type and the year of construction. There you see the yellow bar at the center of the graphs. And that's what happens when you tell the model that you don't know what the type and year of construction is. In that case, the model will make its own assumption and will conduct an analysis based on what you fed into the model. And in this particular case, if it's unknown, if the type and year of construction is unknown, the difference in loss and the extent of the loss can be very, very significant. And the same thing happens not only with the type, but with the year of construction. In different countries, there are seismo-resistant construction codes. These codes are updated regularly every 10 years or every 20 years. And it's very important that this information is represented as it has a huge impact on the results. Here we have a HASTE study on which we have been working with Josefina and the rest of the team. We've aimed to see how we could use that information and improve it and perfect it. We have worked with the ICEMAP engineers. We have analyzed the inspection reports in order to see how we can represent risks better in our models. This is a risk exposed to hurricanes. As for the information that we had the GPS data, the latitude and longitude. We had the risk values, the activity, and the type of construction. This information was fed into the model, and we obtained the result that you can see on the graph depicted in the red line. This is what we call the PML curve that represents the maximum probable loss for different probabilities. And the probabilities are represented in yield and return periods, and the physical loss is represented in figures. If we take this point here and the curve, for this particular point, the risk amounts to $70 million. But little by little, using the reports and the inspections, we were able to add further information, such as the number of buildings, if there are 3 or 4 modules within the same risk. It's very important that we integrate all 4 of them. with their particular features, the number of floors, the year of construction, whether they have protection in the window panes, seeing whether the houses are protected from hurricanes, the quality of the construction, etc. So as we feed into the model this additional information, we obtain better results. And we were able to reduce the PML from 70 million to 25 million in 10 years thanks to the fact that we fed into the model this additional information. We need to understand what the models represent and how they represent what they represent. And the more information we introduce, the better we will be able to handle the risk. To the right, you can see the same case as before. To the left, you have another risk. And there you can see that the sensitivity or vulnerability is different, and depending on where you are, if you consider more extreme events, the difference is much greater at a 1,000-year return as opposed to a 100-year return period. So the idea is to represent catastrophic risk more accurately. In the cases that I explained to you, the PML decreases thanks to the increase in information, but that not always happens. We have some cases in which the PML increases. The model can generate results that are more conservative, and that should be higher. So it's very important that we understand the sensitivity of each model. And last but not least, I'd like to finish with some conclusions. The models are very useful tools to the extent in which they help us understand catastrophic risks and thus manage these risks. However, these are not bell jars or that can help us foresee the future. No, not at all. They're not a window to the future, but they help us understand the probabilities and the loss, what's the probability of suffering a loss. These models are tools that help us manage risk, quantify risk, transfer it. In the reinsurance market, when we manage catastrophic risks nowadays, the reinsurance market aims to quantify that risk and ask information regarding that risk in order to be able to quantify that risk themselves. And also, of course, to mitigate that risk, we need to understand the limitations, the differences, the assumptions on which it is based, and we need to understand how those models represent risk. We need to try to understand that representation. And last, the quality of information, as I mentioned, plays an instrumental role in the management of catastrophic risks. And more particularly, it helps us define the vulnerabilities of these risks. That's all on my side. Thanks very much indeed.
Gracias, Juan. A continuación, Derek Volpert.
Well, thank you very much, Juan. Now we have Derek Volpert, an expert in catastrophes, and he will talk about the new vulnerability models and see how we face reality and these models.
Muchas gracias, Josefina, y bienvenidos a esta segunda ponencia. El título de mi ponencia son los
Well, thank you and welcome to the second presentation. And in the next minutes, I hope I'll share with you the vision of Swiss Re about modeling and modelization. And I would like further on to also mention today's agenda. We're going to start talking about this probabilistic model by Swiss Re to know where vulnerabilities should be placed within these models that we provide. Then we'll see the different activities, how to act when there is a natural disaster. And then we'll get into further details, studying the susceptibilities of precise activity, which is high roads, and how to act when we face an earthquake. And then we see how to model this kind of precise activity. Well, the probabilistic model of Swiss Re has 4 modules. The first is the exposition module. Here we capture all data related to the event. That means level of intensity, hazard maps, and so on. Then the second module, as we see vulnerability. In this module, we capture the sensitivity of the different structures in face of the different earthquake elements. Then we've got distributions. In this module, we say how much of the insured amount is in every area. That is how is shared the amount insured in the area we are analyzing. And then the insurance conditions. Here we capture all deductibles and all limits to the coverage that we are analyzing. All these 4 modules are combined in a model, as Juan already explained, and the result of such a model is this frequency curve that you see on the down area of the slide, and there you see the recurrence frequency as well, and also the period that we are analyzing. If we get into further details, let's see now the different activities and how they react to earthquakes. Well, as Juan England already mentioned, the probabilistic models nowadays have a broad brochure or portfolio of activities, but vulnerability for each of these activities might vary notably according to the kind of disaster that we are analyzing or facing. That is to say, if we see a community building, a 10-story building, and we see the earthquake vulnerability curve, is going to be a very different that curve to the one against the flooding, because basically flooding will affect only like the first floor, but not the whole of the building. What I mean is that you've got like a portfolio of activities, and then you might have different kind of vulnerability curves behind it. Here we're going to focus on activities against earthquakes, because it's difficult to tackle the whole of the vulnerabilities as an ensemble. And I'm going to talk basically about 2 which I consider the most important ones and very difficult to manage, and very different to manage. First, we've got the simple ones, which is just like housing, also commercial risk, communities, and restaurants. And these simple activities are very susceptible to earthquakes, and it depends very much on the kind of different building rules of every country. Later on, we'll talk about that. And then we've got the vulnerability curves for this simple risk, which are usually calibrated upon historical data. This is because the data bank we have is very broad, and the elements are very well defined. This is why it's very easy to estimate the mean damage degree. The mean damage degree means that if you have a 1 million condo, and it suffers 1,000 damage, that is what you will get is like a 10% only loss. So that is the loss you get in relation to the amount which is insured. Then deductibles. They play an important role to give a shape to the vulnerability curves. And it depends on the country and the deductibles in every country. These curves might get more or less of a discount. So it varies according to countries, and this is something which is not always taken into account when doing these models. The importance of deductibles are not always taken into account. The second group we're going to assess here is the complex industrial activities. Here we have very different levels of vulnerability. We've got technological industries with a very high, the highest ratio. And then at the end comes highways and roads. Some of you might be shocked when you see that on the bottom of the list we've got the roads and the highways, and it will be interesting later on to debate on it. And in these complex activities, there is an issue we've got to tackle. Usually, activities where there is a high loss of profit, that is coverage for a big amount, usually those are on top of this vulnerability list. What happens here in these complex activities is that we do not have enough experience. There is very rare experience, and this kind of complex activities is even difficult to state the right amount to be able to estimate the mean average degree. Sometimes they're on a top location, sometimes we've got MLs or PLs, and it is very difficult to really define precisely and correctly the amount of loss in relation to the amount insured, because sometimes these risks are not well defined. So this is part of the issue that we have when we face these more complex activities. Then, something which complements what Juan mentioned. And here I'd like to underline the importance of a detailed information. So this is why I have this practical case to show to you what I mean. Let's assume we've got two hotels in the same earthquake area. If we had no data but these two data, as Juan said, the starting point will be the same for these two hotels, and they will have the same risk premium should we not have any further data about the risks of these hotels. But what happens when we do get detailed information about the risk? There you have the two hotels. They are both in San Francisco, California. The distance in between the two hotels is less than 250 meters. As you might appreciate on the pictures, the risks are fully different. For the first hotel on the left, the Palomar Hotel was built in 1908. It's got 9 stories and the walls are not reinforced. Hotel number 2 is a Four Seasons hotel, and it was built in 2001 after some improvements were made to the building law regulation in California. It is higher, but it is reinforced concrete. And so what happens when we do the model? Well, as you see, starting point in both risk is the same. It is 1.5 per 1,000. And then we add different details related to information. And on the left, the number of floors, the year when it was built, and the walls, which are not reinforced, add a lot of risk premium to this risk. And on the other hand, only the amount of floors add an additional risk, but the quality of building and also the year when it was built add quality to this risk. And this is what is given the difference to these hotels. And I am talking about two hotels that look very alike, and we've got a 2.8 factor of difference, even though they're only 250 meters apart from each other. And now I'm going to show to you a survey that was done by Swiss Re after the Chile earthquake. Here we analyze the whole of the losses reported related to complex risks. And what we can appreciate in this chart on the left is the ratio in between material damage and PVs, business interruption. And what we try to find out is whether there was a certain kind of a model of activity that would be more susceptible to loss profits than others. And, well, as it comes as a surprise, but whatever is the upper side of the chart means a higher loss of profit compared to the material damage. That means that, like all companies, paper companies and food processing companies, they had a higher profit loss rather than material loss. But it is still more interesting when we pay attention to the second chart. There, we appreciate how our internal model was calibrated at the time. And as you can appreciate, should it have been well calibrated, most of the points or dots will be close to the diagonal line, which is where all reported and model data should combine. There we see clearly that reality is very far away for what we included in our models. I've got to mention as well that thanks to the survey and to what we then learned, that's what we call lesson learned after the survey, we fully modified our model for Chile related to profit loss, trying to adapt to what we learned from this experience. What I mean is that in all these kind of earthquake disasters in the last years, if we talk about Japan, we learned that the tsunami is a very important element to take into account, and we added it to our models. Then if we saw the Christchurch earthquakes in Australia and the liquefaction, then we added also these data to the models. So this is something that you also have to sort of keep evolving and adding additional information to them. Okay, we're now get into further details. We're trying to assess the activity of roads and highways. When we see this kind of pictures, and this is from the Taiwan earthquake, it is hard to understand why we think that this is a good risk from the vulnerability point of view, the activities of roads. But if we get into the details of this activity, we'll see that appreciation is not so wrong. If we see the natural disaster risk, usually it is only limited to earthquakes. Of course, some roads might sort of crumble down, or there might be flooding, but it doesn't mean a big risk to a road. And if we compare this to a semiconductor producer where the raw materials and the equipment play an important role, then in roads that content is not very important. It is very difficult to suffer a total loss because roads run thousands of kilometers, and usually it's only a part of the road which is damaged. Well, tunnels and bridges, sub-activities of highways, these are the parts which are more concerned by this kind of incidents, and the coverage is more limited. In most cases, the coverage is limited to material damages. There are some policies which also cover for the profit loss. But since there is not that content that I mentioned, then the coverage is more limited. Then we're going to now get further details about modeling and how we see this from an underwriting point of view. If we do this, we try to see what are the risks that we've underwritten. And what you see here are some highways in Turkey. We have a policy covering these three highways in Turkey. The main highway goes from Istanbul to Ankara. In the second map, we see the earthquake areas or seismic areas in Turkey. It has a high degree of exposure to earthquakes, Turkey, and especially that road that I've mentioned, it is highly exposed to earthquakes. What I would like to underline here is the importance of the distribution of the amount insured. If we get this road from Istanbul to Ankara, the distance is 460 kilometers. And if you see the yellow dots, those are the units to estimate this model. That is the granularity we use to estimate, to make the estimate for this model. So if there is a high degree of granularity in this model, then you can really divide the total amount insured for the highway into sections. And then if we produce these subsections, this has a high impact on our model. If we take chart number 4, these are incident frequency curves. There you see, should we get the whole of the highway as a one only risk, or if we divide it into 4 different sections? It is difficult to appreciate it in this picture, but with this differentiation, what we are doing is making the frequency be on the lower part of the curve. And as we add more risk, we would expect to have a highest frequency of incidents, but the severity of these incidents will be lower. This is just not better or worse. It is only a different way to analyze or to assess the risk. And what is important here is to analyze their consequences. Then, I think this is the most difficult part when we talk about modeling, and this is the profit loss when we talk about highways. As a starting point, we have to have very detailed information. That is very important to know what really makes what really is behind the insured amount. Tunnels, how many bridges, how many kilometers of road. This is very important to analyze properly this risk. Here we had 65% of the insured amount was a highway, and approximately some 16% was bridges with more than 150 meters of a structure. When you say 100 meters, well, it is quite a distance, but I didn't really know what was the risk behind that 150 sort of size of the bridge. Well, we had this bridge which has got more than 150 meters in size. I don't know whether you know this bridge, but it is 1.5 kilometers and it is 165 kilometers above the sea. And if we are talking about profit loss, this is just accumulation of risks. And this bridge it is also important to say that it is the link in between Europe and Turkey. I mean, the traffic flow in this bridge is enormous. What I mean with all this is that when you are doing a detailed analysis of these activities and elements, it is very important to know that you are providing a right risk assessment. And then on the down area of the slide, you've got different pictures of the earthquake in Chile. As you see, according to how bridges are built, they don't react very well naturally to natural disasters. I don't have the time to show you the PV frequency curve, but here we see the biggest differences when you start doing modeling. And if you have like a more of a conservative approach, if you put the whole PV insured amount in every calculation unit, well, the curve sort of bursts out. You almost get a straight line. If you distribute the whole of the insured amount into the different calculation sections, then the addition is very low. And if we go for a further detailed analysis survey, taking into account all these elements like bridges, which really make a difference, then you get this curve which is in between the two. And the difference of the factors was more than 10. What I mean is that we reached the same conclusion as Juan reached, and that is that models sort of provide us some possibilities, but within them we've got many different scenarios that we can analyze, and results might end up being very, very different. So, conclusions we draw. Vulnerability curves are very different depending on the risk of the natural catastrophe and also the activity, the risk insured for that activity. So we advise to go for a risk assessment where you take into account different optimistic and pessimistic scenarios, also to have a very deep knowledge of the different activities, that is an expert know-how, and also to know the specifications of the specificities of every country and of every natural catastrophe. And just to conclude, I would say that all probabilistic models are wrong, but some of them are very useful and helpful, and sort of give us like a wider picture of the risk. Thank you very much.
Gracias, Derek.
Well, thank you very much, Derek. And now we've got Michael Spranger that will share his experience when visiting Japan, Chile, and New Zealand to the places where the earthquakes took place and were damaged. Well, thank you very much, Josefina. It's a pleasure to share some of my real experience on the field or the lessons we learned after the events that took place in the recent years. Some of them have already sort of summed up by the previous speakers. Before I get into the crack of the matter and give you some examples, I'd like to mention something similar to what Juan mentioned. Models, probabilistic models that we are using nowadays at random, are only sort of like newborns. And here you have a list of the accidents that we had when we were very young, because we are in a very a young stage when talking about models. So Norwich Bridge, they almost died there. Those models were not that accepted, and they were so far away from reality that they did not contribute much to our risk assessment. But they did survive in the end. I joined this industry after Kobe's earthquake. I was surprised that the reinsurance companies paid a huge amount of money for events which we could not even think would happen. Kobe's earthquake was a total surprise. It is not a surprise that we see earthquakes in Japan, but there it came as a surprise. And there were many surprises and many chances to learn. What I'd like to share today with you, talking about recent events like Chile, Japan, and Christchurch. Starting with Chile. This is maybe the picture we see more often to show the damages of this earthquake. And from my point of view, this is the last representative of what happened in that earthquake. The reason why we always show this picture is because this is the only or few of the examples of a building that really sort of crumbled down. And if we see the foundations of this building, it is very clear that the thickness of this wall was not right, and also the kind of iron beams that they used were not really good for a place that should be sort of earthquake-proofed or earthquake-safe. On the contrary, in Chile, buildings behaved very well, maybe better than expected. In Chile, constructions are very rigid. You see the walls, as you see down there, very strong with lots of steel inside. So buildings are very rigid, so they move like this. The whole of the building rocks. So damage usually happens on the lower levels. These are the sheet walls that really were damaged. Those are holding the buildings, and they exploded. They bursted out. This is in Viña del Mar, typical damage. And as experts should appreciate here, it is an old building dating back from the 70s. Today, according to building rule, the building law, we know we might expect this kind of damage. So this is why the angle now is 135 degrees minimum, not 90. To precisely avoid what you see down there happening to the steel sticks or beams. And if you see the upper part of the slide, there you've got water deposits, and they were very damaged as well. Then a picture from the other side of the river. And he took it from above, so he didn't want to get his feet wet. But with this angle, you see three bridges. First, the old bridge. I think it dates back from 50 years. Then it was the nicest area, which didn't survive the earthquake. Then the second part sort of had damages, but survived the earthquake, even though it was no longer in use. And then at the end of the picture, you see this railway bridge that sort of went through the earthquake without damage, or without severe damage. There you see the difference on the premium on GPL. And this is one of the lessons we learned. Obviously, we also saw a tsunami in Talcahuano, 7 to 8 meters. It was quite severe, the situation here in Takahama, in Ditarto, where there were like 200 people dying, and it was quite severe. But it was not surprise. The earthquake itself was not an earthquake. There are earthquakes in Chile. We know about it. There are many. It was very long. There was a tsunami. It was not the first one either. The interesting thing here is the frailness of the infrastructure, and also that it had an impact on the electricity supply, water supply, telephones, and so on. I was shocked by the fact that some areas where there were not really many physical damage, but still they had electricity, water cuts. People could not even go to the
la vida en zonas donde realmente no hubo daños. Hubo casi 200.000 siniestros y también mencionado por Derek, las pérdidas de beneficios eran uno de los grandes incertidumbres en este modelo. Pero en total, yo diría un evento, ok, hay que modificar los modelos, hay que modificar las curvas de vulnerabilidad, pero nada que nos sorprendió tanto. Llegó el año 2011, que para mí cambió un poco la perspectiva a esos modelos en sí.
Then there was a change in the approach. As we've already heard, well, the models are good, we learn from them, but then the weak point is exposure. In the year 2011, we saw that it was not the case. There were like 100 million, billion that was insured, but there were not many models, or almost nothing was properly modeled. And then the different disasters, like in Australia, the floodings were not really modeled. For Thailand, for floodings, we know sometimes there are floodings in Thailand. Is there a model? No. Earthquake in New Zealand. We know a lot about earthquakes in New Zealand, but about this particular one, and I will later on give you some details, it was not part of our models. How about Japan and its earthquake? When I was called half an hour after the earthquake, and they told me, have you heard about it? Have you heard it? It's been a very severe earthquake. And I said, like, well, wait and see. Data are going to be correct. It's not going to be that severe. Because scientifically, we think it is impossible to have such a high magnitude earthquake where it took place. Some theories that are learned at university and that make part of these models that say that the maximum magnitude of an earthquake theoretically in this area should be 8.2, 8.4. And that is what we had in our models. 9.0, no way. We did not take that into account. Here you see the red spots. These are the historical earthquakes happening in Japan. There are many of them. And the black areas is where we have very severe previous earthquakes. Those are quite big. And then 2011 came, and this is the rupture area for that earthquake. According to our statistics and theories, that was not possible, and these were the effects of that earthquake. What can we learn from this picture? To me, almost nothing, in fact. It is impressive, yes, indeed, it is. But all you see there is a tsunami that sort of just like washed the whole area. You see some of the foundations of the houses very close to the sea. That is near Sendai, which is the area that suffered most from this earthquake. But then at the end of the picture, you see there a tree, and nothing happened there. So we guess it was like a 5-6 meters wave, and the PML was 5. So this was a rather slow tsunami that washed this area. But apart from the fact that the PML might be of 100, the financial losses were $210 billion. 15% of this was insured, a large part was part of the housing scheme in Japan, and the financial loss was only 7 or 8 that was insured. Same tsunami, 50 kilometers farther north, and it is totally different. This picture was taken at like 18 level above sea level, 18 meters above sea level. In fact, there was a hospital 10 meters behind this picture where this picture was taken, and the ground floor where all the pieces of equipment and all the OR were flooded. So there was at least a high meters high wave, or even higher. I'm showing to you this picture because at the end, on the other side of the mountain, you see some houses which are intact, or the damage there is really restricted to the valley. Still, the image is more aggressive because the speed of the wave there was much higher. Well, something else which was shocking in this earthquake was also the damage caused to what we call content. Here maybe there was a 1.5 meters high wave, and what you see outside is a television, a fridge, the sound equipment, and even the rice boiler. So lots of content exposed there. A big issue after this earthquake in Japan was to say, well, this is a very high, a very important, severe earthquake. How about if there are any after shocks? This is a technical analysis. This was done by some Japanese scientists. It happened basically basically in the northern area, because it did happen on the faults. The west coast moved farther west, so it removed some of the pressure on the faults. So the probability of seeing a new event in the coming decades, according to geologists, will be now lower, or it is now lower. And maybe on the other side, closer to the south of that earthquake, part of that area did not break. That is the area which is in red. So there was lots of talk about whether the new earthquake is going to take place precisely in that red area, and that is very close to Tokyo. So we don't know really. It's quite a logical theory. Apparently, in the red area, there's already like mild earthquakes happening. So it's sort of constantly shaking, but there are not really earthquakes happening. It is not really a rupture that it is taking place spontaneously. What is happening is that it's constantly kind of shaking, as if there was lots of lubricant underneath. So we don't know whether it's going to be like that, but that does have an impact on the PML estimate for the coming years and for the years after such a severe earthquake in Japan. Okay, so what did we learn? The most severe earthquake in the history of Japan, and it was a surprise. It caused a huge tsunami. It was a surprise, but it shouldn't have been such a surprise because, in fact, in Sendai, when you see the sediments, you appreciate previous earthquakes and tsunamis. It seems there had been in the past similar tsunamis. It was very difficult also when estimating damage that the causes were very different, like from the telluric movements, the liquefaction of the earth, the crumbling down, Fukushima, and all, and so on and so forth. Then contingent B proved that it was financially very independent. What did we learn? This model led to the review of earthquake threat models, and not only in Japan. That is to say that there are also now models for these kind of subduction areas. We've got to take into account that we might even now have this magnitude 9 earthquake in Java, in Indonesia, and in Peru. Well, just we now have to take it into account, even though we've never seen it so far. Then the impact on other faults. We've got to modify our seismic threat models. And nowadays, the models related to Japan now have this module on tsunamis as well. And we learned a lot on how to make the vulnerability curves that were already mentioned on the previous presentations. And then my last example, Christchurch. Something totally different. There you have New Zealand, the South Island, the Northern Island. Historic earthquake are yellow, are the yellow dots. And in order to assess the risk of an earthquake in New Zealand, there are basically 3 cities which are interesting. Auckland in the north, around here. Wellington, located here, where there are 4 or 5 parallel faults which have already had magnitude 8 earthquakes, and there's a high concentration around Wellington. And then we've got Christchurch. In the last 20,000 years, no severe earthquake had happened. And somebody called this the tyranny of the obvious. And I like it because some years ago, my work was reviewing the earthquake model for New Zealand. And I spent weeks estimating the maximum magnitude and the frequency of earthquakes in the faults around Wellington. And I just sort of gave 2 minutes to Auckland in the north, saying no, there's no risk there. And I gave no single second of my time to Wellington, because there usually no earthquakes happen, because usually all the earthquakes happen here along this fault. Here we will have all the seismic movement, and here in Christchurch, well, no big deal, nothing to worry about. That's what I thought. It was a big surprise then when in 2010 there was a 7 magnitude earthquake in this green line. The epicenter was in this start here. And this caused a sequence of at least 14 individual earthquakes identified by the Earthquake Commission that pay to the residents the first 100,000 euros of coverage. So 14 events in a year and a half. And this is not part of the models. In the models, they don't show this. They think that all events are independent, and if there is an earthquake, it does not modify at all the PML curve. And here there were 14 events, and the AQC was always paying the first 100,000 euros. And in fact, one of the first aftershocks of the earthquake in Lyttelton caused most of the damage. And there was a total of 400,000 sinisters, and the commission paying this was a company made up of 22 people in the beginning. So it is difficult to know where damages are coming from. And of course, there was a liquefaction. This is one of the main causes of this earthquake. And this is a picture showing what liquefaction means. It means that the floor, the earth sort of liquefies and acts as a liquid, and everything sort of goes down. Thank you very much.
Gracias, Michael, y gracias a todos por las presentaciones tan interesantes. Efectivamente.
Thanks very much for your very interesting talks. We're going to wrap up this roundtable. It's an extremely interesting topic, and I know that you're all very interested, but we need to stick to the agenda. If you have questions, we can have a very, very short Q&A. No? Well, in that case, thanks to our fellow panelists. And we're going to move on with the agenda.